3 minutes. Okay. So we started the second section of a RePAIR project. So my role here is to introduce a little bit of the role of archaeology in this project. Actually, I'm an engineer, but I was a sort of mediator between an engineer and computer scientist and the archaeologist and the restorator. So I will explain a little bit which was the role of archaeology and restoration in this project. So first, well, I would like to introduce one of the two case studies that we are proposing for this project. Actually, the house of a painter at work in Pompeii is located in the insula of the chess lovers. So it's on Via dell'Abbondanza, is the main street in Pompeii. And it's interesting because now we are excavating this area. And it's interesting if you want to continue the visit because in this moment we can see the work going on because the interior block, this insula, is covered with the roof, and with a footbridge you can walk under over the insula, so you can see the restorator work, also the excavation during construction. So this building, at the time of the eruption in 79 AD, was under construction. Actually, there were some damage, probably due to the earthquake in 72 AD. So all the evidence that this work in progress during the eruption, that we found that some caps with some pigments, and also because there is the evidence that the wall have some preparatory drawings that so we realized that at the time of the eruption there was this painter that are working on in the house. So this work was interrupted by the catastrophic eruption. And from this site, we find so many fragments. As you see, there are more than 10,000 fragments. And you see also from Marcello's presentation, they show also Alessio, inside Casina Rustica, there is our lab. We have all these fragments. So you see the picture on the bottom is a picture of our lab where all these fragments. So it's a very hard are located, and this is a very hard task to reconstruct a puzzle starting from these 10,000 fragments. The second case study is the Scola al Maturarum. Also, this building was constructed a few years before the eruption, and perhaps the building was occupied by military association, so we find some depiction of weapons on the walls and so on. This building was very unlucky because during the Second World War was bombed in 1943, and the structure was partially destroyed, and most of the walls and the decoration were lost. So, but between 1944 and 1946, the building was reconstructed. And so we had this wall at a height of 9 meters. But also it was very unlucky because then in 2010, this building collapsed for hydrological instability. So now, then with the great Pompeii project that was financed by the European Union, it started the construction. And so now the building was partially rebuilt in 2019. And now, but we have still now 400 fragments of fresco to reconstruct. And so it's a number limited compared to the one of the previous case study, but anyway, is also this a big challenge. So if you see, Marcello explained the methodology of a RePAIR project that is based on data acquisition, 3D digital modeling, then the puzzle solving, and then the robotic platform that bring each piece in the right position of the puzzle. But, which is our role? So the role of archaeology. So there is so much technology in this procedure, but it is real that obviously also the machine has to learn by human. As I said, we are not only in the human in the loop, as Marcello said in the previous talk, but in certain sense, the know-how of archaeologists should be well transferred to the machine. And so the role of archaeologists in Pompeii, and also not only the group of Fuchs of the University of Lausanne, was to teach to the machine to explain the know-how they have archaeologists in order to develop the puzzle solver. Obviously, you said there is a detached knowledge that sometimes archaeologists feel that by own, but in any case, all this detached knowledge and the traditional way they move are right to reconstruct the puzzle. But also we try to go further because we want to teach also the machine how to recognize the style. Actually, in Pompeii painting, we have a 4 style: first, second, third, and fourth style, and we started to to describe some photos that we have in our archives. And in order to construct a data set of fresco that are annotated in order to, in a certain sense, teach how to recognize the style. From this activity, it was possible to obtain a digital glossary, a classification of the typical iconographic images that we can find on the photos of the frescoes in Pompeii. So we started from a Bible, for archaeologists. It's Pompeii, Pitture e Mosaici, and where there are all the pictures of the frescoes of Pompeii. And we look to these pictures in our digital photographic archives. And in this way, using an annotation tool, that is an open source web tool, we try to annotate each image. So on each photo of a Pompeii fresco, we annotate the iconographic images and describe the type of style that the archaeologists recognize. So in this way, these images with the annotation will be able to be managed by also a machine, a computer science program. You see here the sunscreen of the tools, where some images of photography, pictures of Pompeii frescoes are annotated. For instance, in this picture, you see we have the frescoes of Villa dei Misteri, is a very famous picture of mystery of Villa dei Misteri. That and in this picture we have annotated. We have this box where we annotated the iconographic images, and here you see a human figure floating is annotated for each. So for this, for all the 400 pictures, so we have this data set. It was important to probably, or not only for this project, but we think this type of classification of fresco could be useful also for other purpose, of research, other research purpose, because we have a way to classify frescoes in a way that can be readable by also a machine, an algorithm. So another task that where we are involved, as where the archaeologists were involved, and so to create the information to insert in a data set of the 3D digitization of fragments. Actually, each fragment or each group of fragments has been have a sort of a list of information, reference that give actually all the information needed for archaeologists for the location where it's found, who is the providing institution that have this fragment, and the providing country where is located the fragment, and as well an identification number, the motives, the iconographic images, all the information. So we create for the fragment the metadata in this way. In this way, in this part of the project, the archaeologists give the support to identify all this information. And actually, as a reference, all the Europeana digital cultural platform give us, we try to follow the reference of Europeana. So, and moreover, for this project, we were involved to lead the work package for communication and dissemination, and it was also a hard task for our communication office, actually, because we have to translate this very technological project and to reach a very broad audience, public audience. And that was another important task for the project, because we have also to communicate and disseminate all the results. I'm done, and I give the floor to Plinio, that we come back to technologies and so to the part. Thank you very much.
Okay. Hi, everyone. My name is Plinio Moreno, and I'm going to give you basically a quick introduction about object manipulation using robots, using humanoid hands, and how we can apply these ideas into the manipulation of fragile objects in the RePAIR project. Okay. So first things first, so just to let you know that here we are coming from Lisbon, so the engineering faculty of the University of Lisbon, so I'm actually a researcher there. We have here also Professor José Santos Vitor and a couple of other members from my university. We are in the 140th anniversary, and yes, so we are growing, and we just let you know that we are ready for you to talk also about our school. We have all the engineering departments and also architecture. And also about the research institute. So we are in technical, but we are also a research institution. It's called the Institute for Systems and Robotics. We have, you can see the figures there, 53 integrated PhDs, PhD students. We have multiple research groups. Actually, we belong to the computer and robot vision group. So basically, we try to use vision to provide robots with the right skills to do tasks as manipulation, object manipulation. We have also some other parts, control, intelligent robots, signal processing. Okay, so now I'm going to go ahead with the outline of the presentation. So first, I'm going to give you some motivation about the problem, how difficult it is actually to manipulate these fragile objects. And then I'm going to explain you a couple of approaches that we took into solving this problem. So what we have to consider to grasp an object using a camera, how can we generate those grasping hypotheses, how we can do that with a gripper that is 2-finger and also with a multi-fingered hand. Also, I will speak very quick about how to place fragile objects, or how we can do a motion controller that deals with that. How can we estimate the properties of the object, in this case, the mass of the object, and then some remarks that I will talk about. So starting with the motivation. So this is already a little spoiler about the robot. So you can see here the actual robot that we have here in Pompeii. And the image on the left, you have it's not an actual fragment, it's a printed, 3D printed fragment, so it's a copy of the fragment. And in this case, using a camera, the robot has to select what is the right hand orientation actually to grasp the object. So we have to do that. And to do that, we consider the shape. First thing is a very important clue. So how is the boundary of each one of the fragments? We have to consider the shape. And then, according to the shape, we have to generate what I'm calling grasp hypothesis. That means that what is the right position and orientation of the hand that we have to put that next to the object to actually grasp the fragment successfully. And the other part that is important is we have to place it, and we have to place it in a gentle way, because otherwise the fragment would break. So that's very important. And I'm going to give you like a quick overview of these things. There is an extra thing that I'm also going to talk about, is to estimate the physical properties of the objects from the image. That would also be important for grasping. Okay. So first, starting with the shape geometry for the generation of grasp hypothesis. So let's look at this image. So let's imagine that you want to grasp this bottle. So what you have to do is you have to consider what are the curves in the top part of the object, and to compute some numbers that allows you to actually grasp the object. So we have to look if the object is flat or not, if it have some curves, and what is the size. So we have to match the size of the object to the size of the hand. That's the main idea here. And with just the image, it's not that easy to grasp the object. So you have to actually also have some other information, like the distances or the 3D shape of the object. So in this case, what you see here is a point cloud, that is the points that belong to that image, so the 3D points. And we also want to use that information to decide where to grasp the object. So, and from the left side, for most of you, it's kind of easy to say that I will grasp the object from the top. Nah? For a computer or for a robot, that is not that clear, so they don't have that information. And to do that, so what the robot, the machine has to do. So imagine that you have your hand. In this case, it could be a 2-finger hand or 5-finger hand. And what we have to do is that hand, we have to put it with respect to the object in a certain way. In this case, you can see here 3 hypotheses of the pose. So I can grasp that cap from top, from the left, from the side, and to decide that I have to look into the image and using the image decide what is the right pose to put the hat with respect to the object. And then after selecting the best one, and in this case, for instance, we can say that is the green one, then I go there and execute the grasp. So go there, close the hand, and check if I grasp the object or not. And this part here in the lower part, so this is basically the grasp hypothesis generation. So I can put the hand in different poses, and I have to find the best hypothesis that works for the robot. So we did several experiments. So one of them is with the two-fingered hand. And in this case, as the image that we saw, so is what the computer or the algorithm receives is the image. And then afterwards, I have that image also has a correspondence with the point cloud. And in this case, after looking at the point cloud, we have to select the important part of the point cloud, that is where the object is. So we are removing basically the table that is underneath the object. And then after segmenting the point cloud, what we do is what we call the object completion. So the object completion means that I'm going to basically imagine what are the other parts of the object that are behind the object. So we can only see the front, so we are completing the back part of the object, and the back part of the object corresponds to the red points there in the image. After we complete the object, now we can generate the hypothesis and using the geometry and the shape. So what we do is we simulate placing the gripper in some positions, and the green one on the top is the best one. So it's the one that works best to grasp the object. And what we do afterwards is we execute that. The video is not working. Okay. What happens in this video is that the robotic arm goes there and grasps the object successfully. So somehow the video is not. Okay, so now you can see the arm going there and grasping the object, and it's executing basically the green hypothesis that you see on top of the point cloud. So summarizing, so here we are actually looking into the shape of the object, the geometry of the object, and according to that, we are generating what is the right way of placing, in this case, the gripper, with respect to the object, actually to grasp it successfully. But in this case, it's a very simple hand, has only two fingers. So what we also did was to explore more difficult situations where we have a hand. So we have imagine that you have a hand, and you have to, in addition to the position, orientation of the wrist that you see on the left side, you have also to select what is the right rotation of each one of the finger limbs. So what do we do when we usually grasp objects? That we actually rotate our finger limbs to grasp the object. So in this case, we have a lot more information to consider. So in the gripper, originally, we just have to select the position and orientation once. And in this case, we have to do this for each finger. So it's 3 times more for each finger, so it's a lot more information. And because of that, because of that number of variables, so we have to do it in a hierarchical way. That means that we are doing first some part, and then we're solving then another part. And the way that we discovered that works better is first doing the finger limbs, so the ones that are in blue. So we just first select what is the right rotation of each one of the fingers. And then afterwards, we select what is the position of the wrist. And then finally, the orientation of the wrist. So using this hierarchical approach, we were able to actually generate better grasp hypotheses. And we compare against actually doing all these variables at the same time. And what we can see here is some examples of a robotic hand grasping those kind of objects, a can, a box, and another can. And this idea of basically selecting first the finger rotations, then the wrist position, and then the wrist orientation works better than actually working all the variables together. So in this case, we are running this in simulation with a multi-fingered hand, and we discovered a way that works better for sampling the grasps, what I'm calling the grasp hypothesis generation. Okay, this is the second message that I wanted to convey. Then the third one is about placing fragile objects. That is the case also of the frescoes. So you have to be very careful, because otherwise the fragments will tear apart, will break apart. So and to give a little motivation, so imagine that you want to place you have to place an egg on top of a table. And you have to be careful, because otherwise the egg would break. And what is the approach that we follow? So we humans, what we do, we actually select the right orientation. In this case, for the egg, that is not the best orientation, because it's going to break or it's going to go on sideways. So we have to select that placing pose, that in case of the egg will be sideways. Then we have to measure. We measure the force, the changes in the force, and according to the changes of the force, afterwards we open our hands. And then that is the gentle placing. That is fundamental, because otherwise the object would break. And in the case of the frescoes, that would happen as well. So this is the idea. And what we developed was a controller. So it's basically an algorithm that runs in the robotic hand that is able to consider two things. So when we place the object, we humans do it, we use a lot of tactile information, and we also are using what I'm calling here the synergies. That is basically the coordination that we have between multiple fingers. So we don't control with one finger at a time, we control several fingers at the same time to execute motions. And also, our controller also deals with the orientation, so that means that the force of gravity is also having an effect here, and we have to consider that force in order to measure properly the force that we have to apply or not apply to the object. And consider these three things, so the tactile information, the finger synergies, that's the coordination between fingers, and the orientation. What we are able to do is to have a controller that runs on this humanoid hand, so with 5 fingers, and on the fingertip we have a tactile sensor, and then with the tactile sensors and the coordinated finger control, what we do is actually we release the object at the right timing. And here you can see one video. So in this case, it's placing just this container, and actually is opening the hand at the right timing when it's feeling that the force is decreasing. That's the main idea, and it's using the coordinated finger motion. And you have here, this is another example, and this case is more critical because it's a cylinder, and if you don't release it in the right way, it's going to roll away from the box, but then it does it in the right way because this object is very light. So you see the 2 examples of the controller. Okay. So far, I have explained how to generate grasping hypotheses and how to have a controller that is able to deal with fragile objects. Finally, what I want to talk about is the physical properties of the objects. In this case, is the mass. So it's very important because before grasping, it's very good to know what is the mass of the object, to be able to know how much force I have to exert on the object. If it's light, not that much force. If it weighs a lot, then I have to apply stronger force. That's the main idea. And to introduce that to you, so I want to ask you first, so which of the objects weighs more? So what do you think weighs more? The tennis ball or the soccer ball? Tennis ball, anyone? Soccer ball? Tennis ball, okay. So yeah, so most of the people, they say it's the tennis ball because there is this side weight illusion like from the images, and we tend to basically to give more weight to the smaller objects, so that we have that tendency. But what happens here, so, well, I asked already, so tennis ball, soccer ball, at the end, sorry. So both have the same weight, so that is the truth. So, and so estimate the mass from images for us it could be also tricky. We have this illusion that from that illusion we think that the tennis ball weighs more. And why this is important, we want to be able to estimate the mass from the objects and the robot actually before executing the grasp. So how do we do this? So, well, I already talked about this. So we will have benefits for grasp planning, and because we will apply the right force for the right object, so we will avoid damaging the objects. And the other issue here is that if you use only an image, then we have the problem of not knowing what is the right size of the object. So the image doesn't provide the size in meters of the objects. So what we decided actually to use, in addition to the image, is to use the point cloud. So you have the image on top and the point cloud that corresponds to the object on the bottom. And then using both sources of data, we are going to estimate the mass. How do we do that? So one, we have AI algorithms, and then those AI algorithms, what they do basically is on one side, they estimate the density of the object, and the other side estimates the volume of the object, and we multiply those two, and we get the mass. That's the main idea. And to do that, we need lots of data. We have, let me just show you here. We have here the images. These are the images from the data set. We have images and point clouds from these 150,000 images from Amazon, and then from those images we also have the value, the true value of the mass, and so after putting the machine to learn all this, we are able to estimate the mass using those images, the RGB and the point cloud. So using both types of images is better than just using the image. We are able to run this efficiently, and our average prediction is actually below than the actual object mass. That has to be improved. Okay, so some final remarks. So just to remind you what I just presented, so the first message was the object completion improves grasping robustness. So actually, by completing the objects, we are able to grasp better the objects. The second message is that hierarchical grasp representation works better than actually doing it jointly with all the variables. Then the third one is that I show you a controller that is able to place gently objects. And the final one is that point cloud plus image mass, works better for the mass estimation. So those are all the messages that I wanted to convey here in this presentation. And yeah, finally, so we were here actually doing experiments before, and we were able to pick and place the frescoes in the Casina Rustica. So thank you.
So now the last, Niels Dengler from University of Bonn is.
All right. Hello, everyone. I'm Nils Dengler. I'm a PhD candidate in the University of Bonn in Germany. And I'm presenting now the final integrated robotic system that we developed over the project. So far, you have seen how we were scanning the fragments, how we were puzzling together, but now we need something to actually physically reconstruct the fresco. And you already saw some sneak peeks, but now I give you a better overview over the whole robotic system. And of course, as you can see in the right image, in the left image actually, we take a lot of inspiration from humans, from the archaeologists. For example, here you see that it's better to have 2 hands to handle the frescoes. It's also better to have a 5-fingered hand, as we humans do, and to adjust according to the size of the object, of the shape of the object, how we grasp, how firmly we grasp, and so on. And let's start with our vision in the beginning of the project. So here we were imagining, taking inspiration from humans, that we want to have a system with 2 robotic arms that have a high range of motion, so that we can manipulate a huge range of fresco fragments. Furthermore, we wanted to have adaptable hands that can flexibly change their grasping strategy according to the size and the shape of the frescoes. And we also wanted to be flexible in the position of the robot, so that we have some space that it covers and is not stable at one position. And finally, obviously, to recognize the frescoes, we need some cameras, so that we have an internal representation, or the robot has an internal representation of the fresco position, of the piece, where it belongs to, and so on. And after a lot of conception and manufacturing, we came up with the final system that you can see here. And let's walk you through the individual components in a second. So here we have a workbench which is of 2 meters length, which is covered with sand, which we also got inspired by the archaeologists, because that leads the robot to gently put them on the table and also align them so that they fit in one level. And furthermore, it also makes the grasping easier, because we are able to go underneath the object to grasp it more firmly, but I come to this strategy in a second. Then we have 7 degrees of freedom arms, so that means we can go to very unusual positions where we humans couldn't bend our arm to, so therefore the robot has more flexibility and can reach a bigger range of positions. Then we go to the soft hands. The soft hands are not, they are soft, they're not static. That means they can bend, they can adjust to the fresco's shape and size. And finally, we have the rotation and the translation axis, so that our robot can actually move along the table and bring the frescoes from one side to the other, from the puzzling side to the placing side. And furthermore, we have the camera at the base, which observes the pieces. So let's go through the components in a bit more detail now. So here you can see the robotic arms. You can see how they're move in a great range of motion. We can go to almost any position in this work frame, and this configuration allows for a full 6 degrees of freedom, so all positions and orientations of grasping and placement poses. Then here you can see our hands in a bit more detail. So we actually choose to have 2 separate hands. The first hand is a small hand which we call the QB hand, because it's from the company QB, and it has 5 fingers. They are quite flexible. They are just steered by one motor, so that there's also no possibility of crushing the fresco, for example. They will adapt to the shape and will always firmly but gently grasp the fresco. And in addition to that, we also have the big hand we call the RePAIR hand, which is basically a mimic of the QB hand, but in bigger. It follows the same concepts, but frescoes can vary in a lot of shapes. So they can come in very, very tiny pieces, but also huge 2-kilogram pieces. So we have to be able to manipulate all of those ranges. Therefore, we came up with 2 different sizes, which still follow the same idea of this gently grasping. And here you can actually see them grasping something, working something, and about the whole grasping process I come in a second. And furthermore, here you see them grasping, but how do we actually know that we grasp something? Because when we grasp something and we just go on, at some point we will crush, or if it slips through, we should be able to recognize that it actually slipped and we had to re-grasp it. So therefore, we try to estimate the force that we grasp the object with the hand's current. That means the electrical power that flows during the grasping process. And here you can see some tests we did with a foam and a rigid object. And depending on the object, the current actually changes. But we can say that a safe grasp is established when we have a current of approximately 200, and then we can use that into our pipeline and use this for later use. But also how this current works you see in following videos. And then finally, here you can see that we also took inspiration of how to grasp the fresco from humans, because we don't want to touch the surface. An easy strategy would just be to go to the fresco, put the hand on top, and then grasp. But touching the surface could or would destroy the painting on top. Therefore, we have to be quite cautious. And therefore, you can see on the left some strategies how humans approach that, and this is how we want to do it, or how we did it then with our repair hand. So you can see that there is enough gap between the surface and the palm of the hand, and we are still able to firmly grasp all of the frescoes here. Of course, as you can see, this is just a demonstration by one of my colleagues, but in the end, this was integrated on the real system. Let's come to the system. So our overall pipeline consists of all the parts that were already presented to you and advanced now or extended now by the robotic part. So first we have the detection and recognition of the fresco fragments, and we have the puzzle solving that gives the robot the sequence and the fragments that it should grasp and place in a given order. And this sequence is then given to the motion execution, and the motion execution then defines how to grasp something. And just imagine we are getting this piece in front of us, or the robot gets this piece in front of it, and from the detection we know the bounding box, we know the contours and so on. And how do we grasp the object now? So what is the strategy here? One idea is to just align with the bounding box, go down, and then lift it. The problem is that depending on the piece, on the orientation, on the shape of the fragment, this could work, or as in this case, it will not, because the object will slip, and then we again have the problem with the surface, right? So therefore, here the better idea is to angle with the bounding box orientation, and then we have a way more stable grasp and are able to actually lift the object. And how this looks then on the real robot, you can see here. There you go. Yes, so here you can see now the puzzling of a few pieces. In this example, we actually just sort them, small pieces to the left and big pieces to the right. You can see that the small piece grasp was already successful. Now the big piece comes, and now you actually will see for the second big piece a mistake. So this was actually one of our earlier tries. So here we actually have to help them, and even with the help, it's not 100% working. But when we orient it, then it works in the end. And for the other frescoes, however, now it will work super reliably, and we also improved that behavior now over the last few months. And in the end, you can see that we place them close together so that they will assemble a whole picture. And here you can actually see now the influence of the angle. So one of the big reasons why it slipped was the angle of the object, and when considering the angle, it will succeed. And even if not, you can see now at this fresco that our recovery strategy got more and more reliable. So even though, I'm spoiler now at this point, it will not be able to grasp, it will retry, and eventually will be able to grasp it. There you see. So, and after a lot of testing, we made it as robust that we were confident to also try it on real fresco fragments, because everything you saw so far was on 3D printed ones, on recreated ones, and we also wanted to test it on the real fragment. And here you can see, although it is just a little piece, but you can see on the right, we were highly confident, but also a bit nervous to see how it will look like. But in the end, everything turned out pretty well. And you can see also that all the people that were there when we tried it were super motivated and super impressed how it worked out. And yeah, so you can see due to this claw grasp, the whole fresco was securely grasped without touching the surface, and then brought very safely to the position where it belonged to. Finally, I want to give you a small outlook on what could be in the future, which is not yet implemented, but we already made tests. If we have to grasp the object with 2 hands because it's not able to grasp with 1, we could also do that. You can see here that we use 2 times the small hand, otherwise it wouldn't fit with the dimensions. But then in the end we can also push the objects closer to each other so that the whole fresco assembles in the end. So, and with that I close my presentation. I showed you our advanced robotic platform for shuttered fresco reconstruction. Our soft hands are flexible and gentle for the grasping task. We showed reliable grasping strategies to handle the diverse fragments, and finally also the complete integration from the scanning until the physical placing. This image here is actually 2 years ago from the very first integration where we met in Genoa to test the first baby steps of the system, and from that picture until now there was a huge development. So yeah, thank you for all the help there, and yeah, with this I end my presentation. Thank you.
If there are any questions, so here are the researchers, so they can answer it. In any way, if there are no questions, now we are going to visit Casina Rustica, the lab. We are going to see the robotic system. So we all follow Niels, that now is, for him, it was his house, his home, actually. During these days, also it was raining. Sometimes he was alone, also in this house. And so he knows now the archaeological park better than us. And we go there. After that, we have the lunch, and we come back here around 1:45 p.m. So, and then we continue in the auditorium with the other research projects that are ongoing here in the Archaeological Park of Pompeii. Thank you to everybody. Bye.